Hello everyone, welcome back to Discrete Mathematics with me Adila Krishnadi, and we still in the chat in the subtopic in the topic of bipartite graphs. In particular, we are talking about matching. Now here we have an exercise as described there, and let's look at the solution of this exercise. Make sure that you're done trying and solving this exercise first before we look at the solution. All right, so here's the solution. So we draw a bipartite graph as follows. So for example, this is Sonny, and then you have Tony, you have Winnie, and you have Yenny, and they have a task, requirement analysis, architecture design, implementation and testing, and then the expertise of Sony is architecture design. The expertise of Tony is requirement analysis, requirement analysis, implementation and testing. And then Wenny can do architecture design only, and then Yenny can do requirement analysis, can do architecture design, and can do testing. All right, so do we have a complete matching? So this is V1, the employees, and V2 is the task. Complete matching from V1 to V2. Well, if you look at this for a moment, then you see that it is impossible to have a complete matching. Yeah, no. Why? Because in a complete matching, because if we match, so let me write down it more formally. If M is a matching, involving or where Sony is matched, then Sony must be matched to AD, right? Because that's the only way for Sony to be matched, right? But if this is the case, then of course Winnie cannot be matched, right, to any task. So yeah, so that means M so that means Sony cannot be matched in M. So we find there is a node in V1 that is unmatched by any or that cannot be matched. Yeah, that cannot be matched. So therefore there is no complete matching in the graph, right? So that's the reason. Yeah, so if you look at this more closely, you see that if you match this, then this any cannot be matched to any node, right? Yeah, so regardless whether you could match Tony and Yenny to any other task. All right, so that's an example where we have a graph that contains no matching. Now, well, an additional question to this graph is whether, so what is the size of the maximum matching? Well, the size of maximum matching is actually 3, because you could match, for example, then Tony with RA, and then Yenny with T, for example. Yeah, with the testing. But nobody does implementation then in this case, right? So the maximum matching is 3. The size of the maximum matching is 3, but there is no complete matching from the set of employees to the set of the tasks. All right, so let me stop here, and then in the next video we will look at a theorem that gives us a necessary and sufficient condition of the existence of matching in a bipartite graph.